But when I define what a container does, let me screen here. Everything you're going to see is on Fedora 38. Can people see the terminal window I have here? Okay. So what I'm going to show you here is, if you look at containers, we used to break down containers into 3 categories. The normal processes on a Linux system, but what you want to do is you want to isolate these processes from other processes on the Linux system based on sort of 3 core functionality groups. The first one that most people think about is resource constraints. So you want to make sure one group of processes doesn't dominate the system in such a way that it can't overload the system and prevent other processes from doing what they want to do. In Linux, that's called C groups or control groups. And if you looked at a modern Linux system, pretty much every process on the system, including the one I'm running right now, runs in a C group, and that shows you the C groups that I am currently logged into. And if I went and looked at sysfs C group and took all this information here, cut and pasted it to the end, and when I looked at it, you see a whole bunch of different knobs that I can turn to sort of control what the groups of processes on, from my process and all of my children processes can do. And that's what control groups or C groups are. And that C groups were introduced. When I give these talks, I usually talk about it based on RHEL, Red Hat Enterprise Linux, which is sort of, when we introduce technology into an enterprise level, we feel that it's ready for sort of prime time. So the dates I'll give you, you probably could take 2 years off of that, at about the time they were introduced into Linux proper. But C groups was introduced in RHEL 6 timeframe, which goes back to 2008. So it probably started showing up a little bit earlier than that. The next thing, when you talk about controlling groups of processes on a Linux system, you're going to look at is around security constraints. So if I want to prevent one group of processes from interfering with other groups of processes, I can put them into sort of security realms. And that's been happening in Linux and actually Unix since Unix was started. So you go back to, right when Unix was developed in the 1960s, just thinking of timeshare systems where you have UIDs and what I call discretionary access control, which means you have file permissions on every file object on the system, and then you have UIDs of every process and GIDs of every process, and we control how they interact. Well, there's a whole bunch of other security tools that can be used for isolating processes from each other. Some of those are things like Linux capabilities, which allows us to divide out the power of root. And to give you an idea of what they look like on a Linux system, I'm going to run a Podman command here. So if I just run a general Podman command, cap shell print, this shows you the capabilities that are currently available for a process on the system. So one of the things that when Docker came along, we experimented on what is the Goldilocks moment of capabilities, what you can do with Linux capabilities on a Linux system. And we figured out quickly that Docker figured out that there was about 12 or 14 of them. Since then, Podman's actually shrunk the number down to about 9 or 10 available. Things like being able to change UIDs and things like that. But really what this is all about is limiting the power of root inside of a container. So other things that you can do for security point of view is also use things like SE Linux. So if you looked at, every process on a Linux system, you'd see that all processes have capabilities or lack capabilities in order to do certain activities on the system. And then containers are all about further limiting those capabilities. Similarly, you have rules around SE Linux. So if I did, general process on an SE Linux system has a label like unconfined T, which is, a normal user process able to do certain activities on a system. But I can also run and look at the SE Linux labels that we put on a container, and we can write specialized rules to basically have Podman create containers that have limited SE Linux roles. And what that does is it allows us to basically set up MLS or actually type enforcement rules or SE Linux rules that says that a container can only read and write container content. So if you looked at inside of a container and looked at the content inside of the container, you would see that basically the content inside of a container is labeled as container file T, and processes are labeled as container T, and we write rules into SE Linux that says a container T can only read and write container file Ts. Therefore, if it breaks out of the containment, it cannot attack the rest of the system. Other parts of other security things we have is seccomp, which says that, which basically controls which syscalls a process can interact with on an SE Linux system. So if I looked at what's going on inside of a container from a seccomp point of view, you'd see that seccomp filters are enabled. And what that allows us to do is to eliminate certain syscalls from the container, again, from a security point of view. And one way that a Linux system can attack the host kernel is through the syscall table. So we're taking all of these different security things, and there's more of them. And if you actually do buy my book, chapters 10 and 11 cover all of the different security constraints, concerns that you have when running containers on a system. But anyways, there's lots and lots of security features that we enable for container separation on the system. The last part of container separation is a thing called namespaces. And what namespaces do is basically allow sort of change the virtualization look of a system. So the classic one is, if I looked at my system, you'd see, basically hundreds of processes running my system. I have 482 processes running on my system. But when I run a container, you see, well, this shows shows no processes running on it, but you see two processes running in a container, because with namespaces, I'm able to change the view of the process table inside of the container, or other is mount namespace and stuff. There's a whole bunch of namespaces available. And if I look at every process on a Linux system, I would see that all the namespaces are available to every process on the system. So a normal process is in namespaces. A normal process has all these security controls on them. A normal process has C groups. So when I talk about containers, they're just normal processes on a Linux system with some of these fields changed and modified. Unlike virtual machines, where you're running sort of in some kind of emulation mode or some kind of hybrid environment, container processes are a normal container system. Again, when I was going through the little history there, some of the security stuff, SE Linux was introduced in 2001 timeframe. Seccomp rules were introduced around 2008, 2009 timeframe. And if we look at namespaces, the mount namespace was probably the first namespace that was introduced to the Linux kernel, and that came along in 2006. It was actually in RHEL 5, which was shipped in 2006 timeframe. So there was, a lot of these namespaces and different features of the Linux kernel have been around for a very long time. Give you a little history. I created a thing called the SE Linux Sandbox, which was introduced in RHEL 6. And what SE Linux Sandbox allowed you to do is to run multiple home directories, apps in multiple different home directories. My idea was to isolate different Firefoxes. So imagine you had a Firefox that could only talk to the intranet, and another Firefox that could talk to the internet, and you could sort of bifurcate your desktop environment. And we used C groups, we used mount namespace, we used SE Linux to isolate each one of these, versions of Firefox. We called them sandboxes. We didn't call them containers, but we basically had the idea. So all this technology existed for many, many years, and yet very few people took advantage of it. Very few people could understand how to do it. Around 2012 timeframe, I was working on a thing called OpenShift, which is a way of taking, at that time was time sharing type systems. We were providing systems on the internet where anybody could log on to the system and actually write code for Red Hat Enterprise Linux. But we were taking advantage of SE Linux and other isolation technologies to make sure that all these millions of users that were logging into these systems were isolated from each other. But we wanted to make this technology available to be able to allow them to build applications and then ship them on different products. So we were further looking at some of the technology we had developed at that point, and all of a sudden Docker came along. And Docker sort of changed the sort of the world view of shipping applications in the environment. And what I'm going to do now is I'm going to switch to a part of the presentation. So in 2012 timeframe, Docker comes along, and they really developed two key technologies to make running containers easier. The first one is they developed the idea of a container image. They called it a Docker image, and really what a container image is nothing more than I create a directory on disk, and I put content into that directory, and then I tar it up into a tarball, and I add some JSON to describe what's in the tarball. I push that to a container registry. Docker called it a Docker registry. So it's really a website to store those images. So this allowed developers to bundle the entire operating system together with their applications, bundle in an application along with all the libraries and all the tooling that it would want to use, and then describe how users might run that application, what the entry points are, what the environmental variables, things like that. And that was the birth of a container image. The next thing that Docker really did is they built a simplified tool that could pull those images from a container registry to a local host, and then basically launch, configure all of those container technologies that I just talked about and wrap them around a container. So when I look at what Docker did, yeah, they really took advantage of making simple tools and created a simple workflow for people to ship applications to the world. So now we go. So this all happened around 2002, 2012, 2013 timeframe, and it continued on with this new technology. But a competitor of theirs called CoreOS at the time, this was before Red Hat purchased CoreOS, came along and said, well, this is all fine and good, but we want to run, they had similar technology, and they wanted to run their containers in the world. And they defined a standard called the AppC spec for defining what a container image was. And with that, really what it was is they took the tarball and they sort of standardized on what the fields inside of the JSON file are that describe what the image is. They opened this up to the world and said, this is what we believe should be the standard for running images. And there was a big fair that happened at that point that similar to when Linux started, we had RPMs and Debian packages. We were going to do the same thing again, where we'd have two different image formats available to people. And so all the people who were working on containers at the time decided to get together and form a standards body. And that standards body was called the Open Container Initiative, OCI. And really what happened there is they took the basic format that Docker had developed and standardized it, standardized the fields that go into that JSON file that describes the container images that sit at container registries. And then all of a sudden the OCI image bundle format was created. I like to joke around in the US, there's always these open containers where open containers of alcohol, but when we talk about OCI, we're not talking about that. We're talking about container images. So the next part of my story is around a tool that we we were working heavily with Docker to get different features into Docker. And one of the features we wanted to add was the ability to look at that JSON file that's sitting out at a container registry. So if I wanted to examine a container image, I wanted to examine the content or what a container image was, I would have to do a Docker pull to pull the image down to my host, and then I'd be able to do a Docker inspect to look at the JSON file that's associated with an image. What we wanted to do is be able to just pull down the JSON file. We opened up a pull request to Docker, and Docker basically rejected the pull request, saying that it was making, basically we wanted to do a Docker inspect -- remote, and they said no, that's making the command line too complex. But they said, it's just a web protocol. Like, this is just web files. This is just Apache or HTTP files sitting on a web service. Why don't you just pull it down, write your own tool and pull it down? And so we built a tool called Scopio that could go out and just pull down the JSON file that or the image specification that we could look at it. But that tool eventually not only pulled down the JSON files, but began pulling the images as well, and was able to eventually evolve into a tool that allows you to move images between different kinds of storage. So you could pull images off of registries, pull them to your local machine, store them as tarballs on your local machine, actually pull from images between. And Scopio is a very popular tool for moving images between container registries at this point. So now that we had Scopio, the CoreOS team again looked at that tool and said, well, we'd really like to take advantage of that for our technologies, but we really don't want to be execing out to Scopio. We'd rather just have a library. And in the Golang world, which most of the container world is written in, there's all these sub libraries that are used. So Scopio was broken into two different packages. So Scopio is the command line interface that wraps a new library called containers image. What containers image is a mechanism to pull images between container registries and the host, between container registries. Supports all sorts of transports, including the Docker daemon itself. It can actually copy images in and out of a Docker daemon. So that's where container image came along onto the scene. The next thing, when you pull down these images to your host, you want to store them on disk. Well, the images usually are layered, so they're usually 2 or 3 layers to an image. You might have a base image. Say you have a base image of Fedora, and then you have a web service on top of the base image, and then you might have your application that you build on top of the web service image. And so that ends up being 3 layers. So when we pull that to disk, we need to store that into some kind of storage. And in Linux world, that's called a copy and write file system or a layered file system. And a lot when Red Hat first started working with Docker, we introduced a whole bunch of different mechanisms for storage, including overlay and device mapper. So we took those tools that we had given to Docker and made them into a separate library that could then store, basically store images on disk. And so the final thing when you want to run a container you have to do is you have to sort of define what it means to run a container. So what is the inputs to running a container? And when you think about inputs to running a container, there are really 3 entities involved when you go to run a container. You have the developer who developed the image, the container image that runs on a registry, and that's defined inside of the OCI image spec, right? That JSON file that's sitting at an image. Then you have sort of hard-coded rules that go into the container engine, right? So Docker has hundreds of thousands of rules. It says, what are the seccomp rules for running a container? What are the SE Linux rules? What are the drop capabilities? All these rules are sort of hard-coded into what I call a container engine. And then you have the user input, and the user input can either come in the form of, just command line options when you're executing the tool, or Kubernetes YAML files, or things like that. Or Docker Compose files, but basically they're user input. So the user influences the way the container engine launches the container, and then the developer of the images has some influence. So we needed a way to take all 3 of those inputs and merge them together and define basically how the container is going to get run on a system. And that was also standardized in the OCI standard. And that was standardized the OCI runtime specification. So this, again, is a huge JSON file that gets created when you're on a container. And then there are tools called OCI runtimes. OCI runtime is, the default one was donated by Docker called runc into the OCI runtime. But there's other tools. Actually, Podman mainly uses a sort of a rewrite of runc, which was written in Golang. A rewrite in C was called crun. And then there's other ones like Carter and gvisor, and there's other tools. But basically what these tools do is they read the OCI runtime specification, instrument the Linux kernel, and then launch the container. So when I want to run a container on a system, those are the steps that happen when I want to run a container. I used to protest a lot against Docker, mainly around the fact that Docker loves daemons. And Docker basically had root running daemon on the system, which I thought was, not necessary to run containers. And everything I just talked about in the previous section doesn't mention anything about a daemon, right? I could just write a program that could actually run the containers locally. So I'm going to skip ahead a little bit to talking quickly about a tool that we developed at that time for running Kubernetes workloads. So the original Kubernetes environment was used for running, was used for wrapping Docker and talk to the Docker API all the time. But one of the problems that Kubernetes had when it wrapped Docker was that every time Docker changed, Kubernetes would blow up. So we wanted to introduce a new daemon that Kubernetes could interact with that was tied to Kubernetes, and that became CRYO. And what CRYO did is basically implemented all the steps of running containers, ability to pull, using OCI standards, able to use containers image to pull the image, container storage to store the image on disk, and then launched an OCI created an OCI runtime, and then launched an OCI runtime to read it and instrument the kernel without requiring, basically being tied totally to Kubernetes workflow. So one of the things that CRYO and Kubernetes introduced was the idea of a pod. So a pod is a group of one or more containers running inside of this same environment. In our world, we have a tool called Conmon, which is a little tiny C program that monitors what's going on inside of a container. This allows the container runtimes to go away when containers are run. And here we have an example of a pod with two containers, and actually there's a special little container called an infra container. But what the key feature about these containers is that they share the same namespaces and the same C groups. But the thing to remember here is that there's a little container monitor that's watching each one of these containers and waiting for things like its exit code. If the container exits, records that in data, or waits for someone to connect to it if it wants to get access to the TTYs of what's going on inside of the container. So if we go forward a little further into container history, the next thing that we were looking at was the ability to build these images. So we wanted to be able to not only have images that could go out to container registries, but if I asked everybody in the room right here how to build a container image, you would all scream out Dockerfile. And so Docker basically created a concept of building container images based on a sort of a bastardized version of Bash, right? So but basically it's very popular and everything else. But remember, I talked about container images being a directory on disk that I create content in it that looks like a rootfs, and then I create a JSON, tar it up, and create a JSON file and move it to copy it to a container registry. And yet there's only one way in the world to create these simple objects, and that was using Dockerfile language. And I wanted to basically build a tool to simplify this so that I could just create a directory on disk, copy some content, create a JSON, and push it to a registry. So this guy here, Nalan Daibai, is a guy on my team, and he created probably about 6 years ago. We sat and he's the guy in charge of container storage, and I told him what I wanted, and he said, well, I could probably demonstrate that. And he basically 3 days later had a tool that he could demonstrate, and he asked me what to call it, and I said, I don't care what you call it, just call it Builder. And he made fun of my Boston accent, and that's where Builder comes from. So Builder is a tool, a core utilities tool for building container images, and simply it just becomes a simple command to do Builder from Fedora. So that what that does is it uses containers image to go out to a container registry and pull down a container image called Fedora, pulls it down to disk, creates what we call a container identifier for it. Then you can mount the container image on disk, and then you can basically start copying content into the container. You can DNF directly into the container image. You can make install. When you're done with that, you can actually sort of start to assemble the image. This command here actually adds some of those special fields you see in Docker files, like the entry point and the command line. And then you can commit the image and push the image to any container registry, including Docker IO. And at that point, you'd be able to use this image with any kind of container engine, with Docker, with Cryo, with other builders. So you started to be able to use Builder. And Builder, of course, also supports Docker files, so you can actually build all these container images. But the cool thing about Builder is that it works with Bash as well as Docker files, and just becomes a simplified interface. And our goal with Builder was to make it such that we could just embed it into the other software. So I'm skipping ahead a little bit again. And this talk is really around Podman. So I've really tried to give you some background into the tools that we use to move towards the Podman effort. So I gave this talk a few years ago called Replacing Docker with Podman. And so the steps to doing that are just to DNF install Podman or apt-get Podman, and then do alias docker equals Podman, and then any questions at that point. And the joke there is that when we were defining Podman, we knew that anybody in the world that learned how to run containers would get a Docker command. So if you went to Google and said, how do I do this? How do I run this container? You would get a Docker command. And we didn't want to fight the way that they had defined the CLI, the command line interface to running containers. And so when we were developing Podman, we had to duplicate that entire CLI totally. And a few years ago, back in 2018, a guy named Alan Moran tweeted out, I almost forgot that 2 months ago I had set up alias equals docker equals Podman. Been a dream, no big fat demons. And if you read down on the Twitter page, someone said, what reminded you were running Podman versus Docker? And he said he typed Docker help, and of course Podman help came up on the screen. But the bottom line is all the commands that you're familiar with running Docker are available to Podman on the system. So at this point, I'm going to attempt to do a demo. Hopefully, I've got to go back to here. Okay, so if I'm going to do Podman version, it looks just like Docker version. If I do Podman info, it looks a lot like Docker info. A couple of key things about when I'm doing this, it actually shows that when I do Podman build, it's actually using Builder under the covers, so you can see the Builder version that's imported in here. Here is an OCI runtime. So this is we use the same OCI runtimes that Docker uses. Except we use crun by default, and Docker still uses run C, but Docker can use crun, and you can run C with Podman. So containers we can run any image that's at that's at Docker.io or Quay.io or any one of the container registries, and we run the objects the exact same way. We scroll down a little bit further. A couple of things that are interesting that are different between Podman and Docker is when we were originally working with Docker, this made Docker mad. Docker wanted to hard code Docker.io as being the only way that you could pull images. So if you wanted to use an image that was stored in a registry other than Docker.io, you had to fully specify it, but Docker.io had sort of a special place that you could just say, Podman pull Fedora, and you'd always go to Docker.io for it. Those are called short names. So with Podman, we wanted to support other registries, allow people to block certain registries, and really give control to the enterprise to control what kind of images are. So by default, on Fedora right now, we're set up to pull from 4 different registries, and really it's just a search algorithm. There are some features we call aliases that allow us to alias. So if you say UBI 9, we know that comes from Red Hat, so you'll go directly to Red Hat for that. If you said Arch Linux, you'll go directly to Arch Linux's place for storing that. But in general, if we're just using searches, we will go through and round robin search through the different registries. Here you can see some of the storage for us storing it. By default, we use overlay for storing it, and shows where the storage on system is. But here I'm going to create just a Docker file on disk. And now I'm going to run a container, and inside of this container, I'm actually using Builder. So I'm running a container, and then inside of that container, I'm running Builder to run and develop a container image. Here I am showing you manipulating that container on the system. So basically, I show you can run containers inside of containers. You can run Builder inside of Podman. So everything here pretty much matches up exactly towards what you would see from Docker. But the really key feature that Podman introduced, because it was designed very differently than Docker, was rootless mode. So key thing about Docker is a daemon-based client-server operation. So Docker client, when you run the Docker command, you're actually executing the Docker client and you're talking to the Docker daemon. Podman world, you're just executing the Podman command. So the container is actually a child of the Podman command. And this allowed us to start to run rootless containers. So here I'm actually running in my home directory a command to pull the Alpine image into my home directory. So if I had 50 users on my system, each user would have their own home directories and their images and containers be running in there and totally isolated. So you can run rootful or rootless containers with Podman. Here I am running the container I just pulled, running ls. Here's I'm showing the containers currently on my system. If I'm showing you Podman images on my system, and then I'm running sudo Podman images to show you that it's basically a different list of images. So every user has their own containers in their own system, and there's nothing special. There's no special setuid apps that Podman adds or anything like that. We're just taking advantage of standard tools that are available for the system for running it. So how does this work? How can I have multiple UIDs, right? When I pull down an image, the image could have more than just one UID in it. So how does that work? The way that works in Linux is a thing called the user namespace. What user namespace allows me to do is allocate more than one UID per user. So my user account here is a special file on Linux systems called etsy_sub_uid and etsy_sub_gid. And this says that Dan Walsh has got allocated 65,000 UIDs to his user account, starting at UID 100,000. If you looked at the test one, that's basically setting up 65,000 UIDs starting at 165,000. So what we're able to do is subdivide the entire user namespace or the group of UIDs on a system and start to look at them. So I'm going to run a podman unshare command, and this is basically not running a container. It is sticking me into a user namespace. If I look at my home directory on the system now, you will see that suddenly it looks like all the files in my home directory are owned by root. If I get out of the container and show you the exact same files, you'll see that they're owned by D. Walsh. What's going on here is because I'm in a user namespace that says, I'll show you what a user namespace looks like. It maps my UID, which is 3267, to root inside of the container. So this says map root UID 0 to 3267 for a range of one UID, which means that when Linux system now looks at those files that are owned by 3267, the kernel says, no, that's in your user namespace, that's UID 0. When I look up UID 0, it says it's owned by root. So that's what's going on. And then UID 1 inside of the container is mapped to UID 100,000 for 65,000 UIDs, like I just talked. If I look at this XXX file outside of the user namespace, my home directory, you'll see that it's owned by UID 100,000. And if I'm inside the container, or inside of the user namespace, you see here that it's owned by bin. So that's basically UID 1 on the system. So by taking advantage of user namespace, Podman, enabled this huge leap forward in technology to actually begin to run containers, root-based containers, without being root on the system. So to give you an idea of the power of the user namespace, and Podman has this fully integrated into it, I can actually run a container here. So this one container I launched, so I went back to root because I have more UIDs available. But basically I'm saying I'm going to run, starting mapping UID 0 to UID 100,000 and 5,000 UIDs, just running the sleep command. And if I looked at the sleep command here with a Podman top command, it says inside of the container it's root, but outside it's a normal process on the system. It's UID 100,000, and here I'm doing a PS command to show you that sleep is running as UID 100,000 on the host, even though it's thought to be root inside of it. If I launch a second container using a different user namespace, running the same command, this time I'm mapping UID 200,000 to root inside of the container, and I run the container on the system. Again, you see it is UID 200,000, but now I've run the same container twice. Both have some power of root inside of the container environment, but from the host point of view, if they were to escape to the host, they would be running with different UIDs. So UID 200,000 cannot attack UID 100,000. So by taking full advantage of the user namespace, I can start to get really powerful isolation between my containers. And this is something that Docker was not able to do at the time. And a lot of this has to do with the fork exec model. So the last thing I'm going to talk about the fork exec model is this thing called the login UID. When I log onto a system, the login programs record the UID with the kernel of who I logged in to the system as. So this is saying I logged in as Dan Walsh on the system, but now I'm going to run sudo, so I'm becoming root. I'm running a Podman container, and then I'm going to look at what the login UID of that process is. And it comes out and it says it's still running as Dan Walsh on the system. So even though I became root and launched a container, everything that container does in the system, or all the processes in that container, are going to be identified to the system as being Dan Walsh is doing it. If I do the same command with Docker on my system, it basically generates this huge number here. And this actually is the number -1 as an unsigned number. And what that's telling you is that no one ever logged in and started the Docker daemon. The Docker client talks to the Docker daemon, but the container is a child of the Docker daemon, not a child of the client. A few years ago, I wrote a blog that said that the access to the Docker socket is the most dangerous thing you can do on a Linux system, and I'm going to show you why. So if I ran a container, I'm setting up the auditing subsystem here to watch for Etsy Shadow for people modifying it. Then I ran a container that actually touched the Etsy Shadow file on the host. So this is running a privileged container, mounting the entire operating system, entire file system into the container, and then I'm modifying Etsy Shadow on the system. If I go look at the auditing subsystem here, it shows that Dan Walsh modified Etsy Shadow on the host. If I do the same thing with Docker and run it, Docker will say that it was unset. So it doesn't know who modified the Etsy Shadow file, who launched the container to launch that. And then with Docker by default, if I just remove the container that I launched to, basically if I remove that container, it will remove the log files, and there'll be no record inside of anywhere in the system that said that Dan Walsh modified the etc shadow file. So that's why access to the Docker daemon via rootless commands is more dangerous than giving a user root, because su would record the fact that Dan Walsh became root, or sudo without password, because again, those tools will record the fact that I became root before doing certain activities, and that you could follow the UIDs and via the auditing subsystem. So a couple other features of Podman that we've added is the ability to expose. So Podman top command has all sorts of features for describing what's going on. So what you PID on the host versus what you PID inside of the container. So we're PID 1 in the container, but we're PID 98,000 here. I can show you that. So Linux labels associated with containers. I can show where the seccomp filtering's on. What are the capabilities that are available inside of the containers running with? So another key feature of Podman is that it supports pods. So we talked a little bit about pods when it came to Kubernetes, but Podman also supports multiple pods. So running multiple containers inside of pods. And to show you the power of that, I can actually create a pod, and then I can add a couple containers to it. And now I'm showing you a former container that's running on the system. But if I want, I can actually start the pod, and what that will do is start both containers. So now you'll see 2 more containers get started on the system. And when I stop it, it'll show you that those containers get stopped. So I can actually group my applications together that might be written in multiple containers, so they can all run together on the system. And that's the end of that demo. At this point, I'm going to stop for a second and ask if there's any questions. Anybody have any questions? Yes. Well, I only have a half hour, and yeah. So basically, and there are some questions coming in on the chat, and I'm going to cover Docker Compose in a second. So as you see, what we tried to do is to create a tool that was totally compatible with Docker CLI command line interface, and be able to do everything that Docker could do, but actually relook at it from a security point of view and how we can take advantage of different security features of the operating system, but still be compatible, still be as compatible as possible. So the second part of my presentation is going to talk about sort of where we've gone from that original tool. So that was sort of the state of the art in 2020 and 2021. But as someone in the John O'Rourke has asked, what about Docker Compose? So one of the key things that when we look to replace Docker with Podman, that a lot of people said, yeah, this is great. I can do all my workflows that I can do with Docker from a command line, but I built all this tooling to run, say, Docker and CI/CD systems, or I've built, I'm using Docker PY, which is a Python bindings to launch containers, or I am, Docker Compose is probably the biggest one. So the Docker Compose, which was originally written in Python, these are tools that talk directly to the Docker daemon. They're able to manipulate the Docker daemon to create containers. So people have built huge suites of products to do that, and just having the command line wasn't enough to handle it. So let's go back and we'll start on to the second part of my incredibly quick presentation here. Okay. So this is State of Podman 2022, and I'll talk. I haven't written the one for 2023 yet, so let's just go through it. Everybody seeing my screen? Okay. So I'll give you a quick overview of health of the Podman project. So Podman project, most of this talk goes back to the fall. So at that time, we basically had around 16,000 people have started, 2,000 people have forked it, and I think we're over those numbers now. This is a very U.S.-centric thing, but this is Sally Struthers at the Academy Awards saying everybody likes her. But to give you an idea of how active the two projects are, we're comparing Podman to Docker over a 6-month period, or I think this was 6-month period. Showed that the number of people contributing to Podman were about 2.5 to 1 over Docker. The number of commits were over 2 to 1, around 2 to 1. Number of issues being closed were 2.5 to 3 to 1, and the number of merged PRs were around 3 to 1. So there's a lot more active community going on in Podman at this point. Matter of fact, Docker just released their first version in over 3 years. So Docker hadn't released a version since 2020. They finally released a new version this past May. Past March. So it took them 3 years to get a new release out. So it gets to show that Docker is sort of stalled out at this point, or at least the active development of the server side of the equation has. And Podman has basically been incredibly active over those time. This slide shows you what was going on in 2021 as far as people liking or looking up what's going on the GitHub project with Podman. And you see back in September 21, there was a huge spike in the amount of people looking at Podman. Anybody have an idea what that was? What happened around the first week of September of 2021?
Docker introduced changes to allowances and tried to force people to pay.
Exactly. A bunch of cheap bastards didn't want to pay Docker. And so they were looking for a free alternative to Docker, and that's what happened to Podman. And since then, obviously, Podman's continued to grow, and people are looking at that. So the big question we would get is Podman replace the Docker CLI? What about the rest of what Docker does? And so over the 2021 to 2022, we started to introduce a Podman system service. And what I wanted to avoid a daemon, especially where I sort of made daemons really, really bad. I got people thinking about them badly. But we needed to have what I call socket activation. So a service that would come up for the length of time that you would use to launch a container. And we wanted to have an API that people could talk to, remote API that people could talk to. So we had ended up developing 2 APIs. We have a compatible API, which is totally compatible with the Docker API. So anybody that talks to the docker.sock can actually talk to podman.sock using the exact same protocols. Podman system service will answer those and create containers based on them. And we introduced a Python library that we'll use. So for advanced features of Podman, like pods and other technologies, Podman also has a library for being able to interact with them. Then we introduced Podman Py, which is a Python binding. So if you want to use standard Python bindings to talk to Podman, you can. But we also support Docker Py. So if you've written tools that use Docker Py for everything but Swarm, you can actually use those. And then finally, Docker Compose. So Docker Compose can run against the Podman compatibility socket in both rootless and rootful mode, and you can launch containers using Docker Compose fully with the Podman service. Don't need the Docker daemon to run any of this stuff. I'm not going to do live demos here because I didn't prepare, and I'm probably going to run out of time anyways. I'm already over about an hour. But a couple of things that key about Podman is Podman can not only launch the containers locally as child of the container, but they can also, the actual Podman command can actually has a flag called --remote that could connect to a socket listening on either on the local system or over an SSH connection to another machine. You can manage these SSH connections to remote machines. So Podman can work both, again, locally and over SSH to them. Other machines. So this slide here just shows that containers are really a Linux concept. They're not really, they're There are no Macintosh containers or Apple containers. There are some Windows containers, and Podman does not support them, but almost nobody uses Windows containers. But when people want to build containers, they're usually sitting on a Mac or a Windows box. So they wanted to be able to build Podman containers while sitting on a Windows box, or build container images while they're on there. So Podman introduced the concept of what's called Podman Machine, which really just is a wrapper around virtual technology, virtual machine technologies. So Podman Machine sets up a virtual machine for a Mac or on Windows nowadays. We default to using Fedora Core OS for a core operating system built around containers, and we use simple containers. So if you want to run Podman Machine if you want to run Podman on a Mac, you just do three commands. You brew install Podman, you do Podman Machine init, and then you just start running containers. And Podman on a Mac is automatically defaulted to Podman Remote, so it knows how to talk to the VM that's running Podman service, system activated service inside of the VM. Native installer has been developed so that you can actually run if you go to podman.io, you can get links to install this directly from the website. On Windows, we support WSL, so you can run Podman commands natively on Windows, but it'll be talking to a Podman service running inside of a Linux kernel on a WSL box. And then, so the big thing what Docker was announcing back in 2011, or 2021, was that Docker Desktop you now had to pay for. So Podman has Podman Machine, but since then a new open source project called Podman Desktop was created, and they've made great strides to having a full GUI available for running on Macs, running on Windows, running on Linux. So you can run a very nice graphical user interface that interacts with Podman Machine, interacts with Kind servers, basically does all sorts of ways that you can run containers. It'll actually even work against, if you have Docker Desktop installed, you can actually use Podman Machine to interact with the Docker Desktop. So Podman Machine is a really nice graphical user interface that has really gotten a ton of people using it over the last year or so. It hasn't gone to 1.0, but it's planned to do that by summertime this year. So we talked about Podman supporting Docker Compose, so you can actually run standard Docker Compose agents against the Podman socket activated service. But I actually believe that the way you should be running Podman is to use Kubernetes. I don't like the idea that if you want to build an application to run and you define it with Kubernetes YAML, you have to then translate that to Compose in order to run it locally on the system. So Podman fully supports running Kubernetes YAML files both locally and obviously you can run Kubernetes YAMLs inside of Kubernetes or inside of OpenShift. Kubernetes Podman will actually even generate, so you can go from standard containers on a Linux box to be able to launch, create the Kubernetes YAML files directly from your locally running systems. This shows the command, so you can do a Podman generate kube, which will take your container or a pod you have running locally, and will output all the Kubernetes content that you would need to run on the system. On a Kubernetes system, and then you can do a Podman play kube, which will take a Kubernetes YAML file, say you pull down from Kubernetes, and run it locally on the system. We've added features to Podman play kube to mimic Docker Compose, so you can do things like builds, and that will, if there's a container file or a build or Docker file, will actually build the images and then run them, similar to what Docker Compose can do. And then it has simple syntax like Docker Compose for up and down, taking a container up and down. Similar to what you could do with Compose. So while we fully support Compose, I believe that the future is Kubernetes. Right? Kubernetes won the environment. So if you're going to define a YAML file for how you want to run your applications inside of containers, then I think you should just go to Kubernetes. But for legacy systems of people who've written in Compose, who continue to want to use Compose, we will support that as well. A few years ago, I think the first DockerCon, Docker was very proud to announce that they rejected all systemd pull requests. So Docker didn't believe in systemd. They believed that everybody should just use the Docker daemon for managing services on a system. But Podman was basically looking to be fully integrated into systemd. We wanted to run like normal processes. And because of the fork exec model, we can actually run pretty much standard containers underneath systemd to the system. So we treat systemd as a first-class partner. You can run, if you want to run systemd inside of a Podman container, it runs right out of the box without having to set up anything. Podman is smart enough to know you're running PID systemd as the first process inside of the container. You can actually generate systemd services, similar to how we generate Kubernetes YAML files from running containers. So pods on your system, we can generate systemd unit files based on those. Podman systemd supports a thing called socket activation, which allows you to basically have systemd listen on a socket and then start a containerized service based on people connecting to that socket. And so with Docker, that would never work because Docker was client server. But with systemd and Podman, you can actually use socket activation to pass down the connected socket all the way down to this containerized service running underneath Podman. Another tool that systemd has is what's called SD Notify, which basically allows you to, for the containerized application, to notify systemd that it's ready to receive connections. And again, because of client server, fork and exec model versus client server, that all works in Podman, but never worked inside of Docker. Podman also has full capabilities of supporting auto updates. So imagine you write a containerized service that's going to run on systemd, say on an edge, say on thousands of edge services. Now you push an updated image to a registry. Those thousands of edge devices will phone home and look at the registry, see if there's an updated version of an image available, and we'll go out and pull down the new image to the host. We'll then recreate the container based on the new image and get you auto updated without any users. Then it will run health checks to make sure that the new application came up the same as the old. If something goes wrong on a health check, then it can roll back to the previously running container. So you can start to manage thousands and thousands of edge devices using just container registries and Podman and auto update capabilities built into. So we talked a little bit about Podman on the edge. So this is something I've been working towards, is making containers on the edge, basically thousands and thousands of remote devices better. Since we want to run containers on the edge the same way you run them inside of Kubernetes, we support Kubernetes YAML files. And there's lots and lots of blogs that have been written on that. And I guess at this point, I'm just going to, let me quickly go through what's next. So WASM support has been merged into Podman. So now if you use Podman 4.4 and 4.5, you can actually run WASM-based containers. And Docker has similar to support to this, but unlike Docker, we're running OCI-based containers on WASM, so that the full container tools, drop capabilities, SE Linux wrappers, things like that, are all wrapping the WASM process running on the system. We're also moving towards confidential computing. So there are some blogs you'll be seeing talking about how we can run containerized workloads on a system in such a way that the admin on the system cannot find out what's going on inside of the container. Finally, I guess one of my main goals in doing this is to shamelessly plug my book. And I wrote a book that covers all of these technologies over the last year and a half. And that's Podman in Action. So I'm going to end the formal part of the talk here, and here's the shameless shill to, every time you buy one of these, I get like $3, so it's big money in my future. But anyways, so that gives you a very quick and very dense overview of all the features that are in Podman. There are new features that aren't even covered in the book that are coming along. The newest, coolest one's called Quadlet. And if you want to look for quadlet is basically if you took a kubelet and squashed it, think of a quadlet. And that's really nice new feature for running, again, Podman underneath System D for running services on containerized workload. I mean, it's just basically running containers on edge devices and things. So, do I have any other questions? So you could create containers with Docker Compose and then use Podman generate kube to generate Kubernetes YAML from it. There's actually a project called Compose with a K that does that directly. We don't currently support that, although Podman Desktop might be looking into. But yeah, right now we don't. Podman doesn't automatically convert from a Compose script to a Kubernetes YAML file. You have to go through multiple steps to do it. Excellent. Yeah, I mean, basically you could run, yeah, well, first of all, I don't use the word Docker image, I use container image, but yeah, you push it to a container registry, and then any cloud native application that can deal with OCI images or Docker images, if you force me to say, can actually run them. So we have hundreds of thousands of people are building images with Podman all the time. As a matter of fact, I think all images that you pull down from Red Hat right now are built with container technology, and you can run them very well on Docker or Kubernetes, anybody's Kubernetes, anybody's Docker, any older version of Docker. We are working on improvements for things like pull speeds, adding new features all the time. We do open up pull requests back to Containerd and Docker to make sure we maintain compatibility. We don't want to break compatibility as far as the OCI standards. We want to make sure that we work through the standards bodies to always do that. Our goal is to continue to advance features of low-level container registry. Right, there's a ton of advanced development going on at sort of the Kubernetes and the cloud native. So up in the but at the base level, Podman is really the one pushing the envelope for what can be done at individual nodes. I personally now mainly work on edge devices, so I believe that the real future for edge devices is running containers on, say, thousands of cars, automobiles, running containers, and where windmills running containers on every mile of track. Imagine all manufacturing machines in the future running containers, things like that don't really make sense for a Kubernetes workload. Right, you're not going to be moving containers necessarily around inside of a car and into the cloud. But looking at how we can take advantage of the exact same technologies for running, as I said, more on the edge. And that's sort of where I'm focused at this point. But obviously Red Hat and the container team and most, the large open source community that's behind Podman is working on integrating all new technologies as they come along at the low level. But we don't intend to ever compete against Kubernetes. We don't intend to go cross node or anything like that. And once you get to cross node, that's the world of Kubernetes. Yeah, well, if you I spent almost 2 years trying to write this stuff into a book, so or a year and a half. So if you do have a chance to get the book, and sadly, Red Hat bought the book, so the book is available for free downloads. If you don't want to send me $3 to get it, and spell send Manning. So I will let me. If you Google Podman in Action, you will find I think the second link is from Red Hat, and I think all you have to do is set up an account, and you can download a PDF of the entire book. You can read it that way as well. I'll put the link in there. By the way, if you want to buy the book, if you don't get one of the free copies, buy it from Manning directly. It tends to be cheaper than if you buy it on Amazon. So that's although that also cuts my huge amount of profits per book. Instead of getting $5 a book, I'll get $3 a book. So. What's the one next thing that's going to make people forget about Docker completely and move to Podman? I think it's more evolving than that. So I think as probably Podman Desktop. So the features. So one of the cool things that they do with Podman Desktop right now, I don't know if Docker Desktop does this, but you can sit there and develop your application, develop your containerized application, and then with a single button click, you can go and launch your application into a Kubernetes cluster. So that's probably the coolest thing I've seen done with Podman Desktop at this point. So imagine you have your Windows and your Mac developers sitting there developing applications, and they have simply launching them directly into the cloud or launching them into the CI/CD system, but still can work with them locally and figure out what's going on without having to figure out how they work. And that's the beauty of using Kubernetes YAML to both for local definition as well as remote definition. I can hear you. Well, so I would argue yes. So if you want to, when you run a Podman container, during the time that you're starting the Podman, you're starting the container, Podman needs to run. But when Podman is finished, it basically goes away. And so now you only have the overhead of the container running on the system, plus that little conmon program that's monitoring it. Docker theoretically can do the same thing, but no one ever does that. No one ever shuts down the Docker daemon. And you can simply, anytime you execute the Podman command, or if systemd is doing stuff with the Podman command, then it's going to use more resources. But for the most part, when the system is running in steady state, there is no overhead. There's no memory being used by Podman on the system. So that's I think that's a kind of a really cool feature, that you don't have to have any daemons running on the system. Docker actually supports rootless mode now, but I think it's silly because in order to run Docker, you actually have to run two daemons, Docker daemon and container D daemon doing. So if you want to run a simple container in your home directory, you have to launch up two containers to be running as processes by your user before you can now launch the container, as opposed to just running a command. So if you think about it, in my brain, it's like this is the way Unix is supposed to work, right? Fork exec model. In the book, I try to describe that. So I'm an operating system engineer. So my career has been, basically on low-level Unix operating systems and figuring out how Unix operating systems work. The people who developed Docker came from web services. So they believed in the RESTful API. So they built a tool for running RESTful APIs, services under RESTful APIs, where we evolved a system that ran normal processes on a Linux system. So the perspectives were very different to the teams that were developing it. And the benefit, I mentioned this in the book, is that, Podman came along like 5 years after Docker did, so we were able to look at all the things that Docker did and say this doesn't make much sense. Why don't we do it this way? And so we were able to. We had the advantage of hindsight as far as some of the design goals.